There's a machine being built right now that engineers quietly admit should not be possible. Not in the way that something is difficult or expensive or complicated, but impossible in the way that it breaks the rules everyone else agreed to follow. Rules written by physicists, rules enforced by material science, rules that define the boundaries of what a motor could do, what a car could achieve, what a human being could experience while still sitting on four wheels and staying on the ground. And yet, inside a guarded engineering facility in California, a team of the most unconventional minds in the history of automotive technology is finishing something that will either rewrite those rules permanently or detonate an entirely new conversation about what machines are even capable of. This is not about speed. Speed is just the headline. What this is really about is a decision made years ago, deep inside Tesla's engineering core, to stop asking what was allowed and start building what wasn't. There are moments in engineering history that don't announce themselves. They don't arrive with fanfare or global press conferences. They arrive quietly, buried inside a technical specification document, or whispered between engineers in a break room at 2 a.m. The carbon fiber sleeve that Tesla wrapped around the rotor of its Model S Plaid motor was one of those moments. Nobody outside the industry fully understood what had just happened. The media called it fast. Reviewers called it insane. But the engineers who studied the teardown of that motor, the ones who spent weeks taking it apart piece by piece under laboratory conditions, they used a different word. They called it unprecedented. And what most people are not seeing is that the Plaid was not the destination. It was the proof of concept for something far more extreme that was already in development. Let's go back to where this story actually begins, because the beginning matters more than most people realize. When Tesla was developing the motor for the Model S Plaid, Elon Musk publicly stated that, as far as anyone knew, this was the first time a production electric motor had ever featured a carbon-coated rotor. His words were precise. This is an extremely difficult thing because carbon and copper have very different rates of thermal expansion. To wrap the carbon sleeve over the rotor, it had to be done at an extremely high tension load, something previously impossible to achieve at scale. That last phrase, impossible to achieve at scale, is the one that deserves your full attention. Because Tesla did not just solve a physics problem. They built an entirely new machine to solve it. The machine that wound the carbon fiber over the rotor was created by Tesla Automation, a division based in Prüm, Germany, formerly known as Grohmann Engineering, established in 1983 and acquired by Tesla in 2016. Think about what that means. Tesla did not commission this work from an outside vendor. They did not license the technology. They built the machine themselves, in-house, on another continent, specifically so that no one else could replicate what they were doing. This is not standard automotive practice. This is the behavior of a company that has decided to own a technology so completely that competitors cannot even begin to copy the process, let alone the outcome. And here is where it gets interesting. The carbon fiber sleeve wrapped around the rotor is not a performance decoration. It is a structural containment system. By providing superior containment of the rotor assembly, the carbon fiber wrapping allows the motor to operate at significantly higher rotational speeds, and this translates directly into increased power density, meaning more power can be generated from a smaller, lighter motor. In the world of electric motors, power density is everything. It is the difference between a performance vehicle and a weapon on wheels. And Tesla had just achieved a level of power density that the rest of the industry was still theorizing about in academic papers. A conventional electric motor rotor, spinning at the speeds required for sustained high power, risks deforming under centrifugal force. The material expands outward and the rotor loses precision. Tesla's solution was to wrap the rotor in a layer of carbon fiber, creating a structural band that contains the expansion and allows the motor to spin at speeds that would destroy a conventional design. The result in the Model S Plaid was two rear motors spinning at up to 20,000 RPM, enabling the car to maintain full power output at high speed rather than tapering off, the defining difference between this and every previous performance electric vehicle. Read that again. 20,000 revolutions per minute. A motor spinning 20,000 times every 60 seconds. Not momentarily at peak, not theoretically under ideal conditions, but sustained, consistently, in a production car. That is not just an engineering achievement. That is a categorical boundary being crossed. For context, Tesla's previous 100D model had a red line of 18,000 RPM at 155 miles per hour. The new carbon-sleeved Plaid motor pushes to an estimated 23,308 RPM at 200 miles per hour. The most incredible thing about this motor is the super high red line combined with an extremely flat power curve. Where earlier Tesla motors had a peak power point after which power began to taper off, this new motor pulls hard all the way to its extraordinary red line. This is not chaos. This is engineering precision, executed at a level that makes every previous benchmark irrelevant. But here's where the story starts to split into two completely different directions, and the second direction is the one that changes everything. According to Elon Musk himself, the carbon-sleeved motor in the Model S Plaid is, in his words, the most advanced motor ever used in a street-legal car, rivaled only by specialized lab equipment. And then he added something that the automotive world has been trying to process ever since. He hinted that what we've seen in the Plaid is only the beginning. That sentence, only the beginning, is one of the most consequential statements ever made about electric motor technology, because Musk was not speaking loosely. He was describing a roadmap, and that roadmap leads to a vehicle that makes the Plaid look restrained. The vehicle is the Tesla Roadster, and what is being built for it should not be street legal. It probably should not exist. And yet, as of right now, in June 2026, it is almost finished. On February 28, 2024, Elon Musk revealed what he called radically increased design goals for the next generation Roadster. His words were unambiguous. There will never be another car like this, if you could even call it a car. The sub-1 second 0 to 60 mph time, he said, would be the least interesting part. The least interesting part. A car that reaches 60 miles per hour in under 1 second. Something no street-legal production vehicle in human history has ever achieved. And Musk is telling you that is the boring detail. That is the statistic he is leading with to set the floor of what to expect. Not the ceiling, the floor. To understand why this matters, you have to understand what 1 second actually means in the context of human perception. When a car accelerates from 0 to 60 in 1 second, the g-force experienced by the driver is approximately 7 times the force of gravity. Fighter pilots begin losing consciousness at around 5 to 9 Gs depending on their conditioning and equipment. A production car delivering 7 Gs instantaneously, without warning, without buildup, without the mechanical cacophony of a combustion engine to psychologically prepare you, is a fundamentally different physical experience than anything the automotive world has ever offered. And that is before the thrusters activate. Yes, thrusters. In June 2018, Musk revealed a potential feature called the SpaceX Option Package for the Roadster. This would add around 10 cold gas thrusters to the car to improve maneuverability. The system would comprise an electric pump to recharge an air tank, used to provide compressed air flowing through propelling nozzles to generate cold jet thrust. The air tanks, based on composite overwrapped pressure vessels also used in the Falcon 9 and Falcon Heavy rockets, would replace the back seats. Working pressure would be 10,000 pounds per square inch. Let that sink in for a moment. Tesla is planning to put rocket components, literally the same pressurized vessel technology used to guide Falcon 9 rockets during atmospheric re-entry, inside the frame of a streetcar. This is not a marketing concept. This is not vaporware. SpaceX uses similar cold gas thrusters on the Falcon 9 upper stage for attitude control, so the underlying technology is real and flight-proven in a space context. The question was never whether the technology worked. The question was whether it could survive the regulatory, safety, and engineering challenges of being installed in a consumer vehicle that would be driven on public roads by people who were not astronauts. And according to informed sources within the engineering program, that question is being answered right now. The system is internally known as A71, a collaboration between Tesla and SpaceX. The thrusters are designed to enhance acceleration, braking, and cornering. Musk's claim specifications include a 0 to 60 mph time of 1 seconds, and the ability to briefly lift off the ground. 2 versions are planned, a SpaceX limited edition with the full thruster package, and a scaled-down standard Roadster without the extreme hardware. A car that lifts off the ground on public streets. This is where mainstream media has consistently missed the actual story. Everyone is writing about the speed numbers. Everyone is comparing the 0 to 60 time to Bugattis and Koenigsegg's and Rimacs, but those comparisons miss what Tesla is actually doing. The Bugatti Chiron Supersport uses a 16-cylinder, quad turbocharged combustion engine producing 1,600 horsepower to reach 60 in 3 seconds. It is a masterwork of mechanical engineering representing more than a century of internal combustion development. And Tesla is going to make it look like a family sedan, not with a bigger engine, not with more cylinders, not with exotic fuels, but with a motor wrapped in carbon fiber and cold gas thrusters borrowed from rocket science. But here is where everything changes. And this is the detail that no one is talking about clearly enough. At the July 2025 X takeover, Tesla VP of Vehicle Engineering, Lars Moravy, admitted that the SpaceX thruster system is one of the hardest parts of the entire program. He explained that rocket technology has a high fuel-to-weight ratio, but in a car, mass and a separate propulsion system complicate the equation enormously. Tesla and SpaceX engineers have been working to shift mass where it's needed to make the system work as intended. This is the confession that tells you how serious the challenge actually is. When Tesla's own VP of Vehicle Engineering publicly acknowledges that something is one of the hardest parts of the program, in a program that already involves the most advanced electric motor ever put in a production vehicle, a 200 kilowatt-hour battery pack that has never been built in this configuration before, and an aerodynamic design producing downforce without a fan, when he singles out the thruster system as uniquely difficult, that means this is genuinely uncharted territory. What most people are not seeing is that this is not a company working on a better car. This is a company working on a completely different category of transportation technology, and calling it a car specifically, because there is no other existing word for what it is. Consider the battery situation alone. The Tesla Roadster is claimed to pack a 200 kilowatt-hour battery delivering up to 620 miles of range on a single charge, a figure that, if confirmed in real-world testing, would represent the longest range of any production electric vehicle ever sold. For context, the Tesla Model S Plaid, itself the most advanced Tesla currently available, carries approximately 100 kilowatt-hours. The Roadster is targeting double that, in a low aerodynamic sports car body with a footprint far smaller than the vehicles that currently carry large battery configurations. Squeezing a 200 kilowatt-hour pack into a low sports car body is one of the engineering challenges that analysts have called physically improbable. One Bloomberg analyst stated flatly, years ago, that he did not believe the claimed battery capacity was physically possible to fit inside the car's frame as shown. Tesla has never walked back the claim. Think about what that means. Either Tesla has achieved a breakthrough in battery packaging density that the rest of the industry does not know about, or the final car will deviate significantly from what has been promised. And given what they have already demonstrated with the Plaid motor, the idea that they have solved a battery density problem that others consider impossible is not as far-fetched as it once seemed. The original Roadster prototype aimed for 10,000 Newton-meters of wheel torque, a 0 to 60 time in just 9 seconds, and a top speed exceeding 250 miles per hour, with a range near 1,000 kilometers on the planned 200 kilowatt-hour pack. And then, in February 2024, Musk said those numbers were the old targets. He had radically increased the design goals. The new baseline performance is sub 1 second to 60. The top speed exceeds 250 miles per hour. The wheel torque target is 10,000 Newton meters, which, to put in perspective, is roughly equivalent to the torque that some agricultural tractors produce at the ground, delivered in a 2+2 sports car that weighs approximately the same as a well-equipped Porsche 911. Now layer the carbon-sleeved motor technology on top of all of this, and what begins to emerge is a picture that the automotive industry has not yet fully confronted. Tesla VP of Vehicle Engineering Lars Moravy has confirmed that the carbon-sleeved motor expertise and manufacturing processes developed for the Model S Plaid are committed to the Roadster program first. A carbon-sleeved motor uses a carbon fiber wrap around the rotor to prevent structural deformation at extreme rotational speeds, allowing the motor to sustain maximum power output at high speed rather than tapering off, producing the brutal top-end acceleration the Plaid became known for. But for the Roadster, Tesla has confirmed they are not simply replicating the Plaid motor. Musk has stated publicly that Tesla's team is working on ways to increase the motor's torque and RPM limits beyond what was achieved in the Plaid. If the Plaid motor already redlined at a performance level that makes conventional motors look like toys, then the Roadster motor is designed to exceed even that, and it will do so inside a vehicle that is also being assisted by SpaceX rocket thrust technology. These are not additive improvements. These are multiplying capabilities stacked on top of each other in ways that produce outcomes the industry's current mathematical models are not adequately set up to predict. And this is where the story stops being about a fast car and starts being about something far more significant. What Tesla is doing with the Roadster is not just building the ultimate performance vehicle. They are creating a demonstration platform for a suite of technologies that will eventually cascade through every vehicle they produce. The carbon-sleeved motor, once proven at Roadster performance levels, becomes the architecture for the next generation of Model S, Model 3, and whatever comes after. The manufacturing process, developed by Tesla Automation in Germany, the machine that can wind carbon fiber at extreme tension loads over a copper rotor at production scale, that becomes a proprietary advantage locked behind Tesla's walls, unavailable to competitors, giving Tesla an acceleration in motor technology that rivals cannot match because they literally do not have the machine required to build the component. The potential applications of carbon-wrapped motor technology extend far beyond automotive use. Electric aircraft propulsion is an emerging field where the lightweight, high-power characteristics of these motors could be genuinely transformative. Industrial applications in manufacturing and mining, where energy costs are a significant operational factor, are also being discussed as targets for this technology. This is the part that the auto industry press has systematically underweighted in its coverage. The Roadster is the headline, but the motor inside it is the real story. Because that motor, or the next evolution of it, is going to power things that have nothing to do with sports cars. It is going to power aviation technology. It is going to power industrial machinery. It is going to appear in applications that have not been publicly announced, that are currently being developed in research partnerships that have not been disclosed, because Tesla has understood something that most companies take decades to grasp. The real value of a breakthrough is not in the product you use it for first. It is in every product you use it for next. According to informed sources tracking Tesla's engineering pipeline, the carbon-sleeved motor architecture is already being studied for integration in Tesla's commercial vehicle programs. The Tesla Semi, already one of the most efficient heavy commercial vehicles ever built, could theoretically benefit from a motor architecture that delivers higher power density at lower weight. At scale, this changes the economics of electrified freight transportation in ways that would have downstream effects on logistics costs across entire supply chains. But none of this happens without the Roadster proving the technology at the extreme end, and right now, that proof is delayed. The Tesla Roadster prototype was first shown in November 2017 with a promised production start date of 2020. Since then, Musk has pushed the timeline at least 8 times. At Tesla's November 2025 shareholder meeting, he set a demo date of April 1st, 2026, openly saying that the date gave him deniability. Production was pushed to 2027 through 2028. In March 2026, he shifted from demo to unveil and moved the date to late April. Then, during the Q1 2026 earnings call, he said maybe in a month or so. And then it moved again to August 2026, as SpaceX thruster work continues. 8 timeline shifts over 9 years. That is a pattern, not an anomaly. And the question worth asking is not whether Tesla will eventually deliver the Roadster, they will, but why the delays keep happening and what those delays reveal about the true complexity of what is being built. The demo event is specifically meant to showcase Tesla's collaboration with SpaceX on the cold gas thruster system internally known as A71. The system aims to dramatically increase the vehicle's acceleration and, as Musk has long claimed, allow it to briefly lift off the ground. The delay is not about the electric motors. The delay is about the thrusters. The rocket technology, the component that has never been integrated into a production consumer vehicle before, that operates at 10,000 pounds per square inch of working pressure, that replaces the rear seats with a pressurized vessel borrowed from Falcon 9 rocket systems. That is what is taking the time. That is what is hard. And this is not a failure. This is a company attempting something that no engineering team has ever attempted before, and taking the time to get it right rather than rushing a half-finished product into showrooms and calling it revolutionary. Tesla filed trademarks for the Roadster name logo and its final design silhouette in February 2026. In March 2026, they filed patents for one-piece seats specifically for the Roadster. These are not the actions of a program still in early development. These are the administrative and legal steps taken in the final phases of production preparation. Trademark filings for vehicle silhouettes happen when the design is locked. Patent filings for specific interior components happen when those components are finalized. The delays in the demo date are about the thruster integration, not about the car itself being unfinished. What this means is that we are approaching a moment, sometime between now and early 2027, when the world will see this vehicle in its final form for the first time. And when that happens, the conversation about what an automobile can be will not be the same afterward. The framing Tesla has attached to this Roadster reveal is worth taking seriously as a strategic signal. The phrase being used internally and publicly is the best of the last of the human-driven cars. In the context of Tesla's accelerating push toward full autonomy and robotaxis, that framing is deliberate. The Roadster is not just a performance halo car. It is being positioned as a cultural statement about the end of an era. That framing tells you something profound about how Tesla views its own future. The Cybercab, Tesla's autonomous robotaxi, is the company's primary commercial bet for the next decade. The Roadster exists in a different category entirely. It is not designed for autonomous driving. It is not designed for efficiency or accessibility or mass market adoption. It is designed to be the final absolute expression of what happens when a human being sits in a seat. The Roadster isn't just a performance halo car. It's being positioned as a collector's grade, driver-focused experience. Positioning it this way gives performance enthusiasts a reason to buy without undermining the Cybercab narrative. In other words, Tesla is not confused about what the Roadster is. They are being completely intentional. This is a deliberate farewell to a category, the driver's car, dressed in the most extreme performance specifications ever assembled into a single consumer vehicle. It is the company saying, before we move fully into the age of machines that drive themselves, here is what driving a machine felt like when it was taken to the absolute limit of human engineering. Beyond structural integrity, the carbon-wrapped rotor plays a critical role in dynamic balance and thermal control. Carbon fiber's low thermal expansion helps maintain concentricity under extreme loads. Combined with a skewless laminate design, the result is smooth, pulse-free power delivery, a significant advancement for high-speed motors, smooth and pulse-free, at 20,000 plus RPM, delivering over 1,000 horsepower from 3 motors in the Plaid, and even more in the Roadster configuration, where torque and RPM targets have been deliberately increased beyond what the Plaid achieves. The physics that make this possible are the same physics that were supposed to prevent it, until Tesla found a way to use carbon fiber at production scale to contain forces that were previously considered uncontainable, and now consider the competitive landscape this creates. Porsche has been developing electric motors for the Taycan that are legitimately world-class by any conventional metric. Mercedes has thrown extraordinary resources at its AMG electric program. Ferrari just unveiled its first fully electric vehicle. Rimac, perhaps the most purely focused electric hypercar manufacturer on the planet, builds machines that cost more than most houses and perform at levels that were considered physically impossible 5 years ago. And none of them, not one, has a carbon-sleeved motor manufactured at scale by a proprietary winding machine in Germany. None of them has rocket thruster integration from a collaboration with the world's most advanced private space company. None of them has a motor architecture capable of sustaining 20,000 plus RPM with a flat power curve across the entire rev range. The performance gap between the Tesla Roadster and every other electric hypercar in development is not a gap that can be closed by spending more money or hiring better engineers. It is a gap created by a manufacturing process that competitors do not own and cannot currently replicate. This is not chaos. This is strategy. Years of quiet, deliberate, underreported strategy, wrapped in carbon fiber, pressurized to 10,000 pounds per square inch, and pointed at a performance target that the rest of the industry is still trying to understand. The all-new Roadster sits on a dedicated EV platform and will feature wheel torque of 7,376 pound-feet, 10,000 newton meters, and a top speed of over 250 miles per hour, with an all-wheel drive layout using torque vectoring through 1 electric motor at the front and 2 at the rear. 3 motors, rocket thrusters, carbon-sleeved rotors spinning beyond any previous production benchmark, a 200 kilowatt-hour battery that analysts said could not physically exist in this format, and a price of $200,000 for the base model, which, for a vehicle of this specification, is not expensive. It is extraordinary value for what is being delivered. But there's a final layer to this story that deserves to be addressed, because it is the layer that will determine whether any of this matters beyond a very fast car being bought by very wealthy people. The technology inside the Tesla Roadster will not stay inside the Roadster. It never does. The Model S Plaid was accused, years ago, of being an indulgent exercise in excess. A car that very few people would ever buy, delivering performance that very few people would ever fully use. Built at a cost that placed it firmly outside the consideration set for the vast majority of drivers. And that accusation was true, in every literal sense, but also completely irrelevant to what the Plaid actually accomplished, because the Plaid's motor technology did not stay in the Plaid. The carbon-sleeved rotor architecture, the manufacturing process, the power density breakthrough, these began cascading through Tesla's engineering pipeline the moment the Plaid went into production. Today, Tesla's VP of Vehicle Engineering has confirmed that a tri-motor carbon sleeve configuration is being actively considered for a Model 3 Plaid, a vehicle that would bring this motor technology into a price bracket accessible to a dramatically larger portion of the market. That is the trajectory. Roadster proves the technology at the absolute extreme. Model S inherits it at the luxury performance tier. Model 3 inherits it at the near premium tier. And then, several years from now, after manufacturing scale drives down production costs, some version of this motor architecture appears in vehicles that cost $30,000 and commute suburban families to school and work every morning. That is how revolutions actually happen, not in one dramatic moment, in a slow cascade of technology moving down the price curve until it becomes ordinary, until it becomes invisible, until nobody remembers that there was ever a time when electric motors could not sustain full power at 20,000 RPM, because the carbon fiber that makes it possible is now just a standard feature of how motors are built. We are at the beginning of that cascade. The Roadster is the proof. The motor is the revolution. As of June 2026, the Roadster demo has been moved to August, with production now expected somewhere between 2027 and 2028. The delays continue. The thruster integration remains the hardest engineering problem in what is already the most ambitious automotive program in recent memory. The world waits, again, for a car that has been promised, conceptually, since 2017. But here is the question that should be keeping every automotive engineer on the planet awake at night. If the technology that Tesla has already deployed in the Model S Plaid, A production car you can buy right now, a car that in some configurations costs less than a loaded pickup truck from a premium brand. If that motor was already described by its own creator as the most advanced ever placed in a street-legal vehicle, then what exactly is inside the Roadster? What does a motor look like when a team that built the impossible once decides to exceed even that? What does a carbon-sleeved rotor engineered to exceed 23,000 RPM look like when the engineers who built it are explicitly told to go further? What happens when the people who figured out how to wrap carbon fiber around a copper rotor at production scale, using a machine they built themselves in Germany specifically so no one else could copy the process? What happens when those people spend several additional years designing the next version? Nobody outside Tesla knows the answer to that question. Not yet. The demo is set for August 2026. The production version will follow sometime in 2027 or 2028. When it arrives, and it will arrive, it will not just be a car being unveiled. It will be the end of one argument and the beginning of another. The argument it ends is about whether electric motors can compete with combustion at the highest levels of performance. That argument is already over, and the Plaid ended it. The argument it begins is something bigger and more consequential, about what role the human driver plays in a world where machines are increasingly autonomous, about what performance means when the limit is no longer set by engine displacement or fuel chemistry, and about how far the technology inside a $200,000 sports car will travel, in price, in application, in impact, before the decade is out. The engine was never supposed to be this powerful, and whoever decided to build it anyway may have just changed the direction of an entire industry without anyone fully realizing it yet. Something bigger is coming, and the question is not whether you will feel it. The question is whether you will understand what you are feeling when it arrives.